invited to talk about Ceres, but I thought I would take you through the Dawn mission because I think that there are people on CAPS at the present time that haven't been through this whole story, and it is interesting, and I think there are practical lessons for how to undertake investigations and the process of doing so. So I'll make you suffer through the full story from the very beginning. So why, and I probably don't need to explain to CAPS why we go to the asteroid belt, but some people don't understand why we have to go to the small bodies as well as the larger bodies. This poster that I've got here was prepared for last year's IAU symposium on asteroids, and it's a takeoff on a New Yorker magazine cover. And it shows the asteroid belt as seen from the Earth, as the cover of the New Yorker showed the United States as seen from New York. And, you know, you can imagine that California wasn't very large on that map. And here we have the near-Earth asteroids and then the main belt out there. And Dawn is, exploring this particular region. Of course, we have small bodies scattered all over here, but it's important to get into this region in here between Mars and Jupiter to find out what happened in that a very odd spot of the solar system where the mass density is not exactly what you'd expect it to be. So we are fortunate on Earth because we have samples for a lot of these bodies out here in the meteorites, and we knew an awful lot about Vesta from the samples they sent to us, but we had no information about Ceres, and that was one of the reasons we had to go there, and one of the mysteries of why that particular body, compared to the others, was not sending us any information. Why does Ceres keep itself so hidden from our analyses? Okay, when you design a mission, you have to have some sort of paradigm in mind that of what you're going to see and learn. And our paradigm is that the solar system began a little over 4.5 billion years ago, and that there was at just about that time, as it was coming together, there was a supernova explosion which seeded the solar system with short-lived radionuclides like aluminum-26 and iron-56. And the protoplanets that were accreting at that particular time trapped that heat inside, and that led to melting and differentiation. So we had a set of bodies then that were similar to the Earth in the sense that they might have iron cores and silicate crust. But bodies further out that hadn't been accreting at that particular time they might have got seeded, but the material was could radiate the heat away because it did not accrete into the center. It maybe got a little bit of heating from those radionuclides, but not as much, and so those bodies would evolve quite differently. The model that we were working with was that Vesta was formed with the trapped radionuclides and then got an iron core with a rock exterior, but Ceres was formed later, further from the sun, and did not go through this evolution. So we had a variety of different bodies out in that region, and then Jupiter came together and condensed to form a single gravitational point mass, and that changed the dynamics of the asteroid belt and instead of accreting, they bumped into one another and broke themselves up. But some of them survived. Generally, just as in life, the largest one survived, and the little ones got squashed. We today are left with Vesta and Ceres as the best representatives of what was in the asteroid belt in the beginning. Now, material came to Earth from Vesta. As I said, we didn't get anything that we could recognize from Ceres. Now, beginning with Kepler, that there was a strong suspicion that there was a planet somewhere between Mars and Jupiter, and by the 18th century, that there was a real strong suspicion, and people were looking carefully at that region. And it was Giuseppe Piazzi on January 1st, 1801, who discovered Ceres, the long-expected planet. But unfortunately, more planets were found, and that too many planets were found in that region, and that led to the first demotion of these bodies from planethood to asteroidhood. So along about 200 years later, NASA did something really innovative, and I think it's been very good for the community, and that is starting the Discovery program. And that allows a different paradigm for bringing a mission together. The mission can be more focused in that particular instance. It doesn't have to please everybody. It just has to go out there and concentrate on one particular problem. So Carolyn just told us about some of the results of the Cassini mission. That is, a fantastic mission, but it serves everybody. It doesn't concentrate on one particular thing, and it would be difficult to put that sort of mission together for the asteroid belt. You have to focus on these particular targets with a smaller mission. So I went to the 1992 Discovery Workshop that announced the formation of this program, and there I met an engineer from Lewis, which is now Glenn Space Flight Center, and he was trying to convince us that ion engines were the wave of the future, and you could do all of these different things, but he didn't have any really good ideas of what to do with them. And I went up to him and I said, I think you could do different and better things with these engines, and here's some of the ideas. And he said, well, we got some study money. Why don't you form a little group, and then we'll work on trajectories and stuff. And so we did that. And in 1994, we were prepared to go forward with a proposal to NASA. And I had worked on the moon, and I was during the Apollo program, and I was very frustrated by the fact we had not got back to the moon. But these engines were so powerful, we could go to the moon and do other things too, and leave the moon and go and explore near-Earth asteroids. And so I proposed that, but it was way too ambitious. It had 6 ion engines on it, and a very powerful and perhaps a scary amount of things we were doing. So we didn't win that, and they did select a lunar mission at that time, Lunar Prospector, which was really very simple, and I thought, gee, you could do an awful lot more. I was basically trying to do both Lunar Prospector and Grail at the same time, but they got done separately and done very well by other people. So in 1996, I proposed a main belt asteroid rendezvous that went to Vesta and then two smaller asteroids, Lutetia and Glacenopia, with a small company called CTA, and it was not selected. CTA got bought up by Orbital, so when it came time to propose again in 1998, that I went with Orbital. Now I cut it back a little bit because it was Glacenopia moved out of the way, but I could still go to Vesta and Lutetia. But at that time, NASA or JPL had decided to do a test of the ion engines, and it was just really at a bad time because when my proposal was being evaluated, the ion engines that they had launched, or the ion engine that they had launched on the Deep Space One mission, didn't fire. It eventually did fire, but that was well after the selection was over. So I didn't get that one either. But finally, in the year 2000, I kept sending in that proposal. And this time, Nature had cooperated because Ceres was lining up with Vesta in such a way that a mission could go to one, survey the first one, and then get to the second one. Of course, Ceres being further out was the second. And so we got selected for step one selection, which means that there were three missions that were competing against each other, and we had to, and they were tough competition. So we went into this selection process, and we were scheduled for our site visit on September the 12th, and we were just outside in Dulles, Virginia, just down the road here. And we were practicing when we looked at the TV screens and saw that this was 9/11 and the terrorists had struck. So we realized that we were not going to do the site visit the next day. And so we all jumped in our rental cars and took 4 of them back to LA and drove across the country in 48 hours, driving day and night. But we rescheduled the site visit and started to prepare the mission. We were selected and beat out, they selected 2, and the other one was Kepler. We were selected first, and then Kepler, and then what lost was the mission that eventually became Juno. So it was a really good competition that year, which speaks to the strength of the Discovery program. However, there were budget delays and descopes and cancellations of the mission, 2 reinstatements, fortunately, and later we made it to the Cape. So it was not easy getting NASA to do this. So when we got down to the Cape, then the rocket arrived 11 or 12 days late. So, that cut into the 30-day launch window a little bit. And then when we were putting the rocket together, the crane seized up here, and we couldn't get the strap-ons on. So there's a procedure for fixing the crane, and it takes 7 days. So that cut into the launch window. And then we had a boat that had to be in place in the Atlantic to receive telemetry, or a plane. And the plane had decompression, the window broke or something like that on it, and it had to get fixed. And the boat had engine problems, and it had to go into Puerto Rico to get its engine fixed. And then there were thunderstorms every day. We had an afternoon launch, and we stopped fueling every day because we didn't want something to catch fire. So we didn't launch it. In fact, we let Phoenix go instead, and we were starting to encroach on the Phoenix launch period. So we disassembled the spacecraft and reassembled it in September. Fortunately, in September, we had a beautiful launch. That's the sun over there shining, not the rocket exploding. What our objective is to explore backwards in time and to understand the origin and evolution of the solar system. And to do that, we interviewed two of the oldest members. So that was our philosophy. And we believe that these have been intact since the earliest days of the solar system. And our first test was to test the protoplanet paradigm for the meteorites. And we did test this. And then we went to Ceres and to try and find out what is behind its secrecy. But she'll find out it's doing a darn good job of being secretive. So we used the new technology that we had to do something that had not been done before, which was to go to two bodies, orbit them, and possibly leave. Now the trick here, though, is it was for the cost of a discovery mission. The only way we could do something that ambitious is to use ion propulsion. There's no other. If we did it chemically, it would have cost about $1.5 billion, and there would have been two launches. We did it for under $500 million, so we saved NASA $1 billion. They do not appreciate it even today, yet save them that much money. Okay, let's talk a little bit about rocket science so you understand how that savings come about. On this axis over here, is the exit velocity. This is the specific impulse, but basically you can think of it as the exit velocity of the fuel. And we send the fuel out at about 35 kilometers per second up here. A chemical rocket would be, the fuel would come out about a factor of 10 or more lower. But this axis is thrust. And if you want a lot of thrust coming out of your engine, then you go chemical. We can't, we operate in thrust way down here, a factor of, 10, 100, 1,000, 10,000 times weaker. But we got all the time in the world. So we thrust continually between objects. That does it for us, and we get in. This is what the ion engine looks like. We have three of them. We use one at a time because the grid eventually will wear out. This is our interplanetary trajectory, and we've gone around the solar system a few times, and we're now in orbit around Ceres. We've used over 400 kilograms of xenon and changed the speed of the spacecraft by 11 kilometers per second. Of course, that doesn't mean the spacecraft is now going 11 kilometers per second faster, because it used that speed to change its position in the potential well. So it's actually now going slower. So we went to past Mars. That helped us a little bit by changing the inclination of the orbit and getting a little bit of a gravitational boost. Then we orbited Vesta for about 14 months, and then we went over to Ceres and got there in March of last year. And we photograph the surface. We make topographic maps. We have a gamma ray and neutron spectrometer to get the elemental composition, and an IR and visible spectrometer to do the mineral composition. And we get the gravitational field, and we search for moons. We have not found moons at either Vesta or Ceres. Just another view of the trajectory, and as I said, we're the only spacecraft that has orbited two extraterrestrial bodies, and it was the first to visit a dwarf planet. We beat out Pluto by a few months. Okay, so a typical exploration program is we get into a very high circular orbit. This is a polar orbit, and we let the body rotate under us, and we orbit it. But that's not the important thing. The thing is that the body rotates, and we take lots of pictures of it. Then we move down closer to the body and orbit in survey orbit. That is about, in this particular case, a little bit more than 10 body radii away. Then we get into what we call high altitude mapping, and we do the whole the mapping of the body again, and finally we get into low altitude orbit, and in Ceres cases we're about 374, more like 385 kilometers above the surface at the present time. So we optimize the orbits for different objectives. We do need to, since we've never visited these bodies before, we have to come in fairly carefully to measure the gravitational field so that we can navigate through it. And that when we're trying to take photographs of the surface, it's very important to know exactly where your spacecraft is going. And we've frustrated our public by not getting pictures over their favorite regions because we're just a little bit off on the orbital radius that we were in that gave us a different period, and therefore the interesting regions weren't underneath our cameras at the right time. The HAMO orbit, well, survey is used for the visible and infrared camera optimization, and HAMO we get stereo photography. We optimize for that, and then the low altitude measurements are for the gamma ray and neutron spectrometer and the gravity. We did the same plan for both Vesta and Ceres, and today since I have been here before to talk about Vesta, we will talk about Ceres today. As I said, there are three main instruments: the framing camera, the visible and infrared spectrometer provided by Italy, the camera was provided by Germany, and GRAND, it was the only remaining American instrument after NASA removed two of the three American. So when NASA complains about the dominance of European cooperation on our Discovery program, they've done it to themselves at times as well. Okay, so before we got there, we only had fuzzy images, but fortunately we had HST. HST has been really a great mission for planetary science, and although it wasn't intended that way necessarily at the beginning, it's been used well by the community. And we had at least some information about Vesta from the meteorites. So Vesta was not a surprise. That it turned out to be pretty much what we thought it was at top level. But we learned an awful lot about the collisions, the behavior of that surface, and we certainly did have lots of surprises of what you might call a more minor level, but it was really worth the effort to learn about Vesta. So we're very pleased with what we were able to accomplish. But Ceres, as I said, was much more of a mystery, and we didn't know exactly what we would find. We had Hubble imagery, but wasn't very revealing. When we got to similar resolution on Vesta, on Ceres with dawn, we saw this brightness variation. We saw it turned out to be a small bright region that had not been visible at all with Hubble, and that really got the public involved in the mission. And we got lots of help. The cartoonist jumped in and told us that it was going to be a big inspected by number 6 sticker, but that turned out to be incorrect. We were also told that it looked like a drop flower bag down there, and it certainly did look that way. But I couldn't imagine a way of getting that powder down on the surface from the outside. It had to be coming in somehow from the inside. So the topography of Ceres all by itself was a surprise. We'd expected an icy crust, and it turns out that if you fall on ice, it's pretty hard. But if you just leave ice over millions of years, it sags and flattens out. And so we expected that there wouldn't be. We expected an icy exterior from the thermal models and evolutionary models of Ceres, and there was still a fair amount of topography on Ceres, and it was less than Vesta, but that it's still. It was. This is Vesta. It was less than Vesta, and what was really missing, as you can see, is that there's large scouring of the surface on Vesta, and that is not present. There are some large basins, but it's mainly a lot of smaller craters. So the large craters are missing, and that was that made us think: what is the implication for Ceres interior? It must be much different than that of Vesta, and we will get to that. Okay, so interesting features on the body. Akator has these bright spots. It's taken us a while to figure out what the material is. The first thought was which was based on the visible camera, which measurements, and the camera has limited ability to do spectroscopy, but it was sort of looked like to the camera team that it might be magnesium sulfate, but the Veer team is claiming or identifying these as carbonates, mainly carbonates, probably other things there as well, and it has to be coming from the inside. It's not something that fell down from space on here, and so there must be at least some time in the past, and probably not too long in the past, because these things really do look recent in a geological sense, that it was deposited from below by brine. And then there's this mountain, the Hunamans, and it really does look young. It has cousins that are degraded, and so it's not alone, but it's the best example, and it's like 5 kilometers high, so it's a really good-sized mountain, and it does appear to be fresh. I don't have the exact age for it, but it's a recent addition to the surface. So it must be supported by water ice, and there's lots of good reasons why this is consistent with that particular picture. now, neither of those features are necessarily the youngest. Halloumi crater hasn't got any craters within it. It doesn't seem to have impacts in here, so it's fairly fresh, maybe the order of 10 million years old, and it's got very bright crater floor and surroundings, and it has an extensive ray system, so it stands out on the surface. Excuse me. Now, the interesting thing, and I think one of the important clues about what's going on, are the evidence of flows. Now, to get your eyes straight on this, this is a crater, and this is the crater wall, so the sun is on this side shining on that wall. And if you look down here, you see a shadow. So this material is higher than the surrounding material. This side is the same lighting as this crater wall, and so the flow has come out, a flow has come out of this crater down here. And we believe that these flows happen at times of impacts, whether they're the impact that made the crater or a later impact that melted something. Now, as I said that we'd expect if it was just ice on the surface, that the ice would have relaxed by now at the temperatures of the surface of Ceres. So it can't be just ice, and it can't be just rock, because if rock doesn't do this, not at the collision velocities that you have out there. So it must be a mixture of rock and ice, an intimate mixture, and that when it gets struck, then it will melt and flow. And that is the working hypothesis that we have. I didn't bring gamma ray and neutron data with me. However, let me just say that that we are seeing evidence of water in the crust with the gamma ray or neutron data. Okay, so this gives us a Goldilocks solution that if we do mix rock and ice, then we can explain all those flows that we're seeing on the surface, despite the fact that we've got good topography, high topography, only half as much as Vesta, but still topography. And we have a rigid layer that seems to be strong enough to support craters up to about 200 kilometers diameter. But they're not, there's some features that are larger, but they're not well defined at larger diameters. So we come to a picture of having a hard rock ice layer on the outside that's strong enough to support this sort of topography, but a weaker zone of material on the inside where it's warmer and perhaps has less strength. Now the surface is quite interesting. That it's a lot more complex than the surface of Vesta. There's on crater floors there's complex fracture patterns that not just stress marks that are all parallel, but radiating from different regions and forking and stuff like that. So it's a very interesting body. And there's some regions that almost defy explanation. That here we have a series of sort of valleys, graben, whatever they are, going in this direction. This is Ulodi crater, but we also have structure similar but orthogonal to it. So what is causing this? We're working on it, but it's much more complex than if we were just forming the topography by impact. The surface, this is an attempt at what we call natural color, just not to stretch the color in very odd ways. It give you some impression of what the surface looks like. And it is diverse. It's not just a uniform colorization. So that this is, makes you think that that this body was doing things internally and producing different material and bringing it to the surface in different regions. So we think of this at one time was an active body. This is the albedo. You can see it's slightly different regions of colorization here, but still a varied surface in albedo. And this is from the Veer spectrometer, and here we have looked at the band depth at 2.7, where there are ammoniated phyllosilicates. And if we look at the band where the band center is, there's no variation on the surface. So it's the same material everywhere, but the absorption varies across the surface, meaning that there's more material in some of these regions and less material in other regions. So we have not a uniform surface, but a uniform material. And so the picture that we put together, not to scale, I emphasize, is that there is this stuff we see, a porous desiccated lag layer covering all of the surface. And then there's some more rigid layer of rock and ice that's supporting the outside. And we think that mechanically there's a weaker region inside. How that's evolved with time, we don't know, but that we believe that at least some of the time there was a weaker region down here. And then there's a core whose size we can't define very well with our gravitational results thus far, but we know that there is some sort of condensation in the surface, in the center. So this is a volatile, rich mantle region, and this is our crust. This is the chemistry side of this diagram. This is the mechanical side of the diagram. Now, our biggest surprise, since we were stripped of the magnetometer when the mission was young, that we did not expect to have anything in the way of being able to do something for the magnetic field or for the solar wind interaction with either of these bodies, or explore their magnetism. But we do have the grand instrument that measures electrons and protons and gamma rays and neutrons. In June of last year, there was a solar proton event, and this is just the signature in it, one of its detectors. So that wasn't unusual. We'd seen solar proton events with this instrument before, but for the first time we saw fuzz on here, just small bursts of noise, and the separation here is the orbital period of dawn, and that sort of surprised us. Why would these counts come back with the orbital period. And so we plotted up where those events occurred, and they occurred at the same spot each of 3 orbits. They weren't correlated with the surface topography. The body just rotated under us, and nothing on the surface was doing this. But this is solar coordinates. This is we're going across the subsolar point here and going over the poles to the other side. Now it turns out that eventually the PI of the grand instrument realized that he had other detectors scattered around his instrument that were sensitive to electrons, and they were on different sides of the spacecraft and not pointing in the same direction this detector. And in fact, we see bursts all the way around the orbit. It's just that these things are directional, and they're coming from basically the direction of Ceres, but somewhere around it. And so we've seen events like this on Earth by spacecraft near Earth when the magnetic field lines up with the bow shock, and so that we believe that there was a temporary bow shock formed on this particular day associated with that solar proton event. And when the spacecraft finds itself on field lines that are tangent to this bow shock, then the particles get accelerated and get back to the spacecraft. And this mechanism will provide you with bursts on every side of Ceres if you're looking in the right direction. So our explanation for that is that there was 2 possible explanations. There could be a magnetic cloud that comes out with the solar wind flow and then magnetizes an ocean or an ocean of salt water or brine inside, and then that magnetic field would diffuse in on a certain time scale as long as that external field is there, and then it will decay on the same time scale. We haven't got a magnetometer to say that there was a magnetic cloud there, but there's a good possibility. The other possibility is that the solar proton event, when it irradiated the surface of Ceres, it liberated gas that had been absorbed on the surface, and that it had a temporary atmosphere, and the time for an atmosphere on Ceres to decay is about a week, and those calculations were made before we got to make these measurements. Okay, I did bring a movie, and I don't know whether we can play that movie. Did you check that out? Go down to the bottom? No? Okay. Then there. Okay. I do have it on a stick if you want to see it, or if we're running out of time. Have we got time? Okay. Yeah, that's the last. Sure.
So, Chris, why don't we go open it up for questions, and then while we're getting the movie ready, and then we can come back to the movie. Jim?
Yep.
I'm not sure if you answered the question of why we have samples from Vesta but not from Ceres, or if you did, I missed it.
I was too subtle. But I didn't do it explicitly. We're not producing big craters on Ceres because that at the large impact size, we're not, the material is breaking up basically, and so if the material comes out, then it must be friable. It's not big chunks of basalt that it's just it's just diffusing out through the solar system. It comes into the Earth's atmosphere. We don't recognize it. So we don't have chunks of basalt coming off the surface.
I can be a little more specific. We're probably lucky that we get the pieces from Vesta from what may have been a recent giant impact, what's called the Rhea Silvia Basin. And Vesta is a little more dynamically favorably located to get stuff to Earth. It's closer to inner asteroid belt.
However, if it weren't for some difference in the material, I think we'd have a few meteorites from even Ceres, and there's nothing that we can identify with Ceres. And this hasn't helped us, we say, aha, that's what we should have been looking for. We haven't found, we didn't have that aha moment yet.
Other questions?
Yeah, Chris, I was going to ask you, any idea what the salts are? We heard about salts and brines at Enceladus, and now maybe we've got salts and brines at Ceres. And are we talking about any of the same things? Carolyn could jump in here, too.
Yeah. Bethany, do you want to take that?
Yeah, so I've been working as an affiliate with the Dawn team. So it's really interesting that these bright spots are actually spectrally different, one to the other, when looked at the visible and infrared data from the VIR team. So we're just in the process now of writing those up to publication. In fact, I was proofreading the publication on Tuesday for submission. So, for example, Akator crater has what appear to be sodium carbonate and ammonium chloride salts in it, as well as different compositions of hydrated minerals like phyllosilicates and the rest of it. And I believe that the idea the sodium carbonates and the ammonium chloride salts are consistent with the types of chemistries that have been observed on Enceladus, for example, where there are chloride brines that are interacting with materials that are in some cases ammoniated. So that's exciting. But and I don't know, Chris, you should jump in at any point, but in some of the other craters, Oxo crater, there's spectral evidence that's more consistent with water, ice, and or a very hydrated sulfate or chloride salt. So they do appear to be different.
Okay. Other questions?
So, Chris, is there any evidence from any of your data sets and any of your orbital campaigns that would correlate with the report of plume, OH plume, by the Kuipers et al. paper?
We can't say that there isn't, but there's nothing really clear to us that we've seen that seems to be a temporary phenomenon. We had one at the beginning. The camera team thought that they saw haze that was periodically appearing each day in Akator crater. However, we don't have any supporting evidence for that, and they're just the same few images that were taken from a distance and in a particular angle. And so, and we haven't seen any transient phenomena. We've looked at the Hubble data and compared it with our data, and we feel that the Hubble data and our data are consistent, and neither of those sets show anything that is time varying. So we cannot on the project support any of those other observations. They're looking at something we can't look at.
Okay, so in the Washingtonese, you can neither confirm nor deny?
Yes, exactly.
Okay.
All right, movie ready? Okay.
So that's what you can do with a discovery budget.
All right, we still have a few minutes before a break. If anyone has one final question. Okay.
Yes, Carol.
Well, I think you didn't say, or maybe I was spaced out, and you did say it. This whole idea of salts on the surface is pretty exciting, right? And you're telling me you've aged, with crater statistics, you think one of these places is 10 million years old. Any ideas of what might have happened at that time to bring salts up to the surface? I mean, water, right?
Yeah,
it's water
really, yeah. One of the problems we have is the time variation. We really do not have a good time story yet on any of this. And, some of the team believe, things are happening every day. Some of the team, think, well, it's, a billion years old or, so we don't know, we haven't got the age dating story down
But it's not impacts into an icy shell that just exposes salty ice and then the water evaporates.
It certainly doesn't look that way. That Akator, I didn't bring that slide, but Akator, that central bright part is a dome that's all fractured with a pit around it. But we don't have anybody that stepped up and said, I know how that dome was made.
Aren't there domes? Aren't there salt domes in Arches National Park?
Sure. I mean, there's diapirism. I mean, I think I'll just expand on what Chris has already said and said, like, this is the most active area of discussion in the team right now. Does it mean that all of these salts were formed sort of early and they occupy some of a layer underneath this rock ice mixture and they're just being excavated? Does it mean on the far other end that there's activity today, even like salt diapirism or phase changes driven by some sort of unknown heat source? Or does it mean that there's impact-induced hydrothermalism that creates these brines, which then come to the surface? That is another hypothesis that's been put forward. So I think the answer is going to be somewhere in between those three things. And what's exciting is we're still continuing to get the highest resolution data from VIR and FC now. Like, the data collection at the highest resolution is still continuing. So I think we'll be able to use some of the geology to differentiate